Professor Rad here, and today we're going to talk about independent events. So two events are independent if the occurrence of one event does not influence the occurrence of the other event. So this would be something like some independent events might be, let's say I select a card from the deck of cards, and then I flip a coin. Whatever card I drew from the deck of cards has no impact whatsoever on whether I get heads or tails when I flip the coin. So those two events would be independent. Something that might not be independent could be the shirt I choose to wear today and the slacks I choose to wear today. So if I select the shirt first, that may impact the color or type of pants that I'm going to wear. And vice versa. If I'm like, I really want to wear these jeans today, what shirt's going to go well with that? So knowing one thing impacts the likelihood of something else. So those two events, what shirt I'm going to wear based off of what pants or vice versa, those would not be independent events. We can see this concept occurring in the formulas for independent events. So if two events are independent, then a conditional probability is the same as just the straight up probability. So for example, the probability that I get heads on a coin, given that I pulled the three of spades, is going to be the same as the probability that I flip the coin and get heads, right? It'll still be 50-50. The three of spades has nothing to do with the coin flip. Now, if I know that two events are independent, I can take the conditional probability formula and rearrange it to get this situation here. So my recommendation for this formula is not really to use it that often, in the same way that when we had mutually exclusive events, the probability of X or Y, we didn't have to worry about subtracting an and. That's really great for mutually exclusive events, but only mutually exclusive events. This formula is really great for independent events, but only independent events. So we're going to use it, but I don't think of it as using the formula. I think of it as, oh, I'm in an independent event situation. This is the process that I use. So let's go ahead and look at a couple of examples. So for this first example, they're telling us the probability of V is 0.3, the probability of W is 0.4, and the probability of V and W is 0.12. And we want to know if V and W are independent. One way to do that is to use this formula and check to see if it holds up. So I'll work through this problem two ways, but one way is to use that and formula. Okay, now we're interested in V and W, so I'm just going to go ahead and change all of the X's and Y's to V's and W's. And I have this question mark here because that's what we're checking for. I don't know that they're equal yet. I'm checking to see if they are. So the probability of V and W is 0.12. And I want to know, is that equal to 0.3 times 0.4? So when we check this one out, they do end up being equal. So yes, V and W are independent. So if I multiply out 3/10 times 4/10, I end up getting 12/100. So they are equal. So these are independent events. If I got something like 0.16 here, so it was something different, then they would not be independent. Then they would impact each other. Another way to see if two events are independent or not is to use a conditional formula and see if you get the same thing. So for example, I could say, is the probability of V given W, is that the same as the probability of just V, whether W has happened or not? So the probability of V given W, I'm going to use that formula for the conditional probability. So that would be the probability of V and W. over the probability of W, since that was our given condition, is that equal to the probability of V? So the probability of V and W was 0.12. The probability of W is 0.4. And we want to know, does that equal 0.3, since that was the probability of V? So if I do 0.12 and I divide it by 0.4, I do indeed get 0.3. So yes, V and W are independent. So that's how I could check with a formula, a different formula, using the conditional probability formula. So let's go ahead and look at an example of determining whether events are independent and using this formula not so much as a formula, but kind of as a process. So in this example, Alice has a weighted coin so that it comes up heads 25% of the time. So when we say a weighted coin, what we mean is maybe there's like a heavier metal placed on one side of the coin so that when you flip it, it's more likely to land with that side down. So the coin that Alice has probably has a weight on the heads side so that it comes up tails much more often. In this case, are the events independent? Yes, they are. Okay, because even though it's more likely to land on tails than it is to land on heads, whatever I get the first time I flip the coin is not going to impact what I get the second time I flip the coin, right? I'm just as likely to get heads 25% of the time, no matter what I got before. So for part B, let's complete this probability distribution. Because we know that heads happens 25% of the time, that will have a 0.25 probability. And sort of the complement to that, tails, would be 0.75. So remember, you can find that by doing 1 minus 0.25. For part C, it says Alice flips the coin twice. We want to determine the probability that she gets heads on the first coin flip and tails on the second coin flip. So in this situation, we're going to take the probability of heads and then tails. So I'm going to put and then here just as an emphasis. So this is going to be the probability of heads times the probability of tails. And this is because of this formula up here. This would be the probability of heads on the first coin flip and the probability of tails on the second coin flip. So we have probability of heads times the probability of tails. So that's where that formula is coming into play here. So I'm going to take 0.25 and multiply it by 0.75. And I'm probably going to get a long decimal here. Yeah, I get 1875. Now, the reason I said I think of this as more of a process is because I want to be careful not to confuse the probability of heads and then tails with the probability that I flip the coin once and I get both heads and tails on that coin flip. So this and then is actually pretty important for this process. So instead of thinking of it as an and formula, I think of it this process that no matter how many times we're flipping the coin, so if I'm flipping the coin 5 times, that means I'm going to multiply 5 probabilities together. So this is representing heads, heads, tails, heads, heads. So I'm going to take the probability of heads times the probability of heads times the probability of tails times the probability of heads and times the probability of heads once more. So whatever sequence of events we're looking to achieve, that's going to be the sequence of probabilities that get multiplied together. So this is looking like 0.25 times 0.25 times 0.75. Oh gosh, okay. Getting quite a long decimal here. This is what I got. Now, because of that, Very often when you're multiplying lots of decimals together, you're gonna get a gnarly decimal answer, really long. And we weren't told to round this one, so I'd have to write that whole thing out. So what would be better is actually to use fractions. I know, a time when fractions are better. 20.25 is the same as 1/4. So we'll take 1/4 times 1/4 times 0.75 is 3/4 times another 1/4 times another 1/4. Now, the reason that fractions often work better in a situation like this is because when you multiply fractions, you multiply across the top and then across the bottom. So we can get our solution pretty easily. We've got a bunch of 1s times a 3. So we'll have a 3 for the numerator. And then we have a bunch of 4s in the bottom. So 4 times 4 times 4 times 4 times 4 is going to give us 10/24. So our final answer here could be the fraction 3/10/24, or it could be this really long decimal, depending on, the mood we're in at the moment, I guess. All right, so that's going to conclude this video about independent events. So in fact, this is going to conclude our section on discrete probability. So I hope you found probability interesting. And if you found it not interesting, don't worry. Our next unit is on some totally different stuff. So we have a chance, kind of like with a clean slate for the next unit. So I hope you have a fantastic day, and I'll see you in the next one. Bye for now, everyone.